Hello, my dear friend. Welcome to the course Modern Generative Adversarial Networks. My name is Denis Volkhonsky. In this course, we will mostly talk about Generative Adversarial Network, the framework that was proposed in 2014 and now has state-of-the-art results in generative learning. Now you can see on the slide the progress in face generation that was made since 2014. The first image, which is the gray person, is a result of using standard generative adversarial networks. However, from year to year, people improved the quality of the generated images, and on the right of the slide, you can see the result of state-of-the-art generative adversarial networks, which is called progressively growing GANs and its modification. And all these we will study in our course. You can see the other amazing application of GANs is the interpolation between different faces. And we again will study all these in our course. After taking this course, you will understand how to build generative adversarial networks that are able to generate such a high quality images that you see on the picture. All of these images are synthetic and there is no one real object. Here you can see the progress that was made in generative learning for ImageNet dataset. ImageNet is a dataset that contains 16 millions of images from 1000 classes, and you can see what people can do now, like generating very realistic dogs, sea, burger, and any other classes. The model that generates such a high quality images is called big GANs, big generative adversarial networks, and we will study this model in our course. In our course, we also will study a lot of applications of generative adversarial networks. Here you can see the transfer from the sketch to the generated image. There is some tools where you can draw a sketch and obtain a generated image from this sketch. Another application of generative adversarial networks that we will study is image-to-image translation. When we have image of one type, for example, summer, and with generative adversarial networks, we translate this summer image, summer photo, to the winter image, and back from winter to summer. Also, we can translate the photos to the drawings and the drawings to photos, horse to zebras, and in fact many other applications. This is not all the applications that we will study. We will cover a lot more, like super resolution, in painting, and many others. This course will be rather hard, and I expect you to have knowledge in building neural networks with any library like PyTorch, TensorFlow, and Theana, or something else. I hope that you understand basics of linear algebra, probability theory, and statistics, and you are not afraid of such words as probability density, Kubo-Kleber divergence, and any other. And I expect you to have a great wish to study modern generative adversarial networks, because my focus is to share with you my knowledge in state-of-the-art generative adversarial networks, how you can train them, how you can build them, and how you can do it efficiently in order to obtain your results and maybe to solve your practical problem. In our course, we will have 4 main blocks. First block is introduction that you are now listening. I will describe what is generative learning and why do we need it, and what are the existing approaches for generative learning. In the second module, we will study standard and convolutional generative adversarial networks. So after the second module, you will be able to generate realistic photos of people of size 64 to 64. After the third module, you will know a lot of applications of generative adversarial networks like image translation, image in painting, image super resolution, and many others. And in the last section, in the fourth, we will study state-of-the-art generative adversarial networks, which is called progressively growing GANs and big GANs. I will share with you all my experience in these state-of-art GANs, and after that you will be able to build your own GANs to solve your own problems and to generate whatever you want. Thank you and see you in the next video. In this video we will talk about generative learning and density estimation. We will consider different applications of generative learning and different types of density estimation. Machine learning can be divided into two big parts: discriminative learning and generative learning. Discriminative learning is such problems as classification, regression, and many others, and usually in discriminative learning our goal is to estimate the distribution P of y given x. It means that the given object x, our goal is to predict some label for it. It may be a class label or a regression label. In generative learning, usually we have a set of samples x, and our goal is to estimate the distribution P of x. Another possible variant of generative learning is conditional distribution estimation. When we have a set of objects x and labels y, our goal is to estimate the distribution P of x given y. And sometimes in generative learning we want just to estimate the distribution. Sometimes we want to have the ability to sample from this distribution. And while building generative adversarial networks, we want to build a network that will allow us to sample from the distribution P of x or P of x given y. Now let's consider, why do we need generative learning? There are many possible applications. The first application is generation of realistic samples, of realistic images, which can be used in some articles or books or papers. The second application is complex probability distribution estimation. So usually we have a set of data and we want to somehow estimate the distribution of these samples. And these samples can be of any type: audio, images, texts, and for some reasons, for some maybe other algorithms, people sometimes want to estimate this distribution. Here, generative learning helps. The third application of generative learning is simulation of the future, for example, for reinforcement learning. So if we have a pose of a person in the current moment, what will be his pose in the next moment of time? And that's where we can use generative learning. Another possible application is filling missing values in our data. As you know, in practice, sometimes we don't know some features, and what people can do is to insert just average values or even delete these rows from the training set, but the good way will be to predict the missing values and to insert them, and here again we can apply generative learning. The next application of generative learning is when we have a lot of data but only a few amount of labeled data, as you can see on the bottom image. Now we have two dots labeled and others are unlabeled, and here we can also apply generative learning in order to pre-train the classification or regression network. Another possible application is text-to-image synthesis. Imagine that you write a book and you would like to insert some illustrations to this book. And imagine that you build an algorithm that takes the text as an input and returns some generated images, which you can insert into your book. And that's the application that we will study in our application section. The next application is image in painting. Imagine that you have an image and you would like to delete the person from this image. What you should insert instead of the person? Could we do it automatically? And the answer is yes, and I will tell you how we can do it. Next application is super resolution. Imagine that you have an image that is very small and you would like to increase its size. And if you just do it in the program like Photoshop that use nearest neighbors method or some other interpolation method, you will obtain very low quality image. But using generative learning and generative adversarial networks, you are able to increase the size of the image and have a high quality as an output. In fact, this is not all the applications, and we will consider much more. I just tell you that we are not limited in just generation new cats and dogs. There are a lot of really useful practical applications. All generative learning is based on density estimation. It means that usually we have a set of training samples. It can be images, sound, text, or any others, and we would like to either build density function or have an ability to sample from this density. And we can divide estimation of density to two types, implicit and explicit. While we use implicit mode, the likelihood usually is not available at all, and density function is also not available. But we can sample from the distribution that we estimate. And the good example of this approach is generative adversarial networks that we study in this course. Using generative adversarial networks, you can't tell what will be the likelihood and you can't estimate the density explicitly, but you can sample from the distribution and obtain, for example, images that are similar to the images in your training set. And the other type is explicit generative models. Usually, they are built with likelihood maximization, and usually we have this likelihood function, and we have density function of this distribution that we estimate, but we not always can sample from the distribution. The good example is kernel density estimation, when we estimate the density of the distribution using some kernel like Gaussian, but we are not able to sample from it. And now the most popular generative learning are built in the following way. We have some generative model, which is usually a neural network with some convolutional or linear layers. We have some noise as an input, which can be sampled from random uniform or normal distribution. And as an output, our network gives us some faces. That is all for this video. Thank you and see you in the next one. In this video, we will study what is generative adversarial networks. Imagine the situation. There is a counterfeiter and a police. Counterfeiter tries to make fake money in order to deceive the police. On the other hand, the policeman tries to distinguish between real money and fake money. And in fact, this is the idea behind generative adversarial networks. We have two neural networks, generator and the discriminator. Generator tries to generate a realistic object, realistic image. Discriminator tries to distinguish between this generated object and training object, real object. So discriminator is a binary classifier which has two classes, real and fake, and tries to learn the difference between fake class and real class. On the other hand, generator tries to deceive it. As an input, generator takes some random noise from some distribution like normal distribution or uniform distribution or any other. It is a learnable function, usually it is a neural network, and the discriminator is also a neural network. Both generator and discriminator has its own parameters which are learnable and learned with stochastic gradient descent or its modifications. The input of the generator could be the noise from any distribution and of any size, so it can be a vector of noise. And the output is synthetic sample. The input for the discriminator is an object, in our case it is image, and the output, the probability of this image to be real or to be fake. So discriminator outputs one probability as a binary classifier, probability of image to be real. Let's look at the last function of the generative adversarial networks. Let's assume that d of x is the probability of x to be real. G of z is generated sample, and z is some random noise. Now we consider the loss function for the discriminator. The first term stands for the probability of a real x from the data distribution, p data, to be real. And we want to maximize this probability. This is why in the last function we have this term with minus sign. We minimize minus this probability. The second term stands for fake objects. Now we want to minimize the probability that our synthetic object, which is g of z, is real. We would like to minimize this. That is why we have there 1 minus d. To summarize, when we optimize the discriminator loss function, we maximize the probability of a real object to be real and of fake object to be fake. This is just the standard loss function for the binary classifier. If we consider the loss function for the generator, we again look at the feedback of the discriminator only on synthetic objects. So what we do here, we generate some objects from z, g of z, and then give it to the discriminator. And now we maximize the probability of synthetic sample to be real. It means that if we maximize this probability, then our discriminator will fail in prediction and will not distinguish between real class and fake class. This is all for this video. In the next video, we will consider algorithm of training generative adversarial networks. Thank you and see you in the next video. In this video, we will study the algorithm of training generative adversarial networks. The training of GANs is divided into two parts, updating of the discriminator and updating of the generator. For each iteration of our training, we k times update the discriminator and 1 time update the generator. This rule was proposed in the original GANs paper. However, now things changed and people usually do in another way, which I will show you in the next videos. However, now let us study the original algorithm. So, as I said, for each iteration of training, we update the discriminator k times. In each of these updates, we firstly sample m noise samples from some prior distribution, which can be uniform distribution, normal distribution, or any other. After that, we take some m random samples from the training set. So if we have a set of training images, we take random m samples. And look, now we have two classes. First class is fake class. In order to obtain it, we use z1 to zm and use them as an input to the generator, and the generator outputs a set of objects which we assume to be fake. And the second class is class of real object, which we just took from the training set. Since the discriminator is a standard binary classifier, we use binary cross entropy loss. Mention that now here is the word ascending in the algorithm. It means that in order to use gradient descent, we should put minus here. Anyway, let's look what is happening here. This is real object, and d of x is the probability of x to be real. So we maximize the probability of real x to be real, and here we minimize, because of this minus, the probability of fake object to be real. So in other words, we maximize the probability of fake object to be fake. This is, I think, rather obvious and is a standard practice for training binary classifier. We now can average this loss function and compute its gradient. This formula stands for the discriminator updating, and we do k such updates, where k is a hyperparameter which of course can be selected. Then we switch to the updating of the generator. We again sample a batch of noise samples from our same prior distribution, which, remind you, uniform or normal or any other. Now we do the opposite to what we did in the discriminator update. We maximize the probability of fake image to be real. It means that we train our model in such a way that we deceive the discriminator. But now we don't touch the parameters of the discriminator at all. We just use its feedback. And in this line, on this step, we just update the generator weights. In order to summarize the training of generative adversarial networks, we k times update the discriminator, 1 time update the generator, and when we update the discriminator, we use standard binary cross entropy loss and update it as a standard binary classifier. When we update the generator, we again use the discriminator's feedback, but touch and update only generator's weights. But we choose the opposite direction and do it in such a way that the discriminator will fail in its prediction. That is all for the standard algorithm of training generative adversarial networks. Thank you and see you in the next video. In this video, we will study how we can build a generative adversarial network that will approximate normal distribution. As a noise for generator, we will use uniform distribution. So first let's import necessary libraries. Then we have two functions, getUniform, which is in fact our noise, and getNormalDistribution, which is a normal distribution with mean 5 and standard deviation 1. Note that the size of these distributions is batch size to 1. It means that it's just a vector. Now here we have two classes, generator and discriminator, and both of them are PyTorch compatible. And Now we have to write a code for the main sequential module. So here I propose to use two linear layers. Here we have in features 1 and the intermediate features, let's say it will be 16. Then let's add some nonlinearity. Then again linear layer. And in features 16, because it's an output from the previous layer, and out features 1. So, and we expect that after training, this generator will transform the uniform noise to the normal samples, to samples from the normal distribution. Now we have to write the discriminator. So here we again can use two linear layers, linear in features 1, out features, let it be the same, 16, then nonlinearity, then again an n.linear in features 16 and out features 1. And here we have to return the probability of x to be a real class. That is why we can and we should add sigmoid function here. So sigmoid will transform our logit that is an output from the linear layer to the probability. And here we create two objects for generator and discriminator. After that, we should define optimizers that will optimize generator and discriminator. And usually people do it separately. So one optimizer for generator and one for discriminator. Now, here we have to write two functions. First, for updating the discriminator, and second, for updating the generator. Now, what we have to do here? We sample real data, compute probability of real object to be real, then sample noise, obtain generated object, compute probability of fake objects to be fake, and write loss function. So let's do it. In fact, what we do here, we want to build binary cross entropy loss using the annotations from the lectures. Real samples will be just get normal function, batch size. This is our real samples. Now, the probability of real object to be real. In fact, it is just discriminator from real samples. And that's it. This is because I defined that discriminator of x is the probability of x to be real class. So, and this is what we want. Now, we have to do something with generated samples. We have to obtain noise, and for this purpose we use get uniform batch size here. Then generated samples is just generator from noise. And in order to obtain the probability of these fake samples, generated samples, to be fake, we need to write 1 minus discriminator from generated samples. Why 1 minus? Because discriminator from the input returns the probability of this input to be real class. So the probability of input to be fake class is 1 minus the output of the discriminator. Now we have to write loss function here. Let's think. When we train the discriminator, what we want? We want to maximize the probability of real class to be real, right? And we want to maximize the probability of fake class to be fake. That is why we should do the following. When we use PyTorch optimizers, we usually minimize, but we would like to maximize. That's why we just put minus sign before probability of real class is real and minus sign of probability of fake class to be fake. Here we should add logarithm torch.log, and here again torch.log in order to obtain proper loss function. And so here we are, we maximize this, that's why we minimize minus this logarithm of probability, and the same with this probability. And now what we have to do in PyTorch is to write .min, because this is a vector and we should obtain a scalar value for our loss function. Good, we are done with the discriminator. Let's now switch to the generator. We again should obtain noise, get uniform. We should obtain generated samples. It's just again generator from noise. And now we have to obtain probability of fake class to be real. This means that we should write discriminator from generated samples. And that's all. This is because discriminator, as I said, returns the probability of input object to be real. So we give it fake object, like here, and the output is probability to be real. So we are done. And now the loss function, what should be? We should maximize the probability of fake class to be real. Generator wants to maximize the probability of fake class to be real. It will mean that the discriminator will fail in its predictions, and a generator can fool it. That's why we write minus again torch log prob fake is real, and we have to write again .min here, and that's all. And here we have zero gradient, then backward pass, and then do optimization step. And in fact, that's all. Now we have a loop for the training. What we have here? We have the number of updates for the discriminator on each iteration. Here it is used. So on each iteration we update 10 times the discriminator and 1 time the generator. And we should tune this parameter and have batch size 64. Now let's run this loop. Error, get uniform, should obtain batch size, yes, batch size. And SNS is not defined because I forgot to import Seaborn. Yeah, that should be right. Now what we can see here, orange is our true distribution and blue is our approximation of it, the output of the generator. And our goal is to make them closer to each other. Now, the green line is the probability that is the output of the discriminator. So you can see that the distributions after training became approximately the same, and let me stop it, and the P from real data starts to be near 0.5. It means that if the discriminator output the probability 0.5, it means that he can distinguish two classes, real and fake. And in fact, this is what we wanted. We obtain samples that are generated that are very close to real distribution, and discriminator fails to distinguish them for these values. So in fact, this is not the ideal approximation. However, as I said, we can tune this parameter, and let's say it can be 50, and let me add the code for limits for y. So we add it here, and let's restart the kernel and run all cells again. So I set 50 here, and let's change to 300. And I added limits on y. So we restart it and run everything else. Now you can see this is the distribution that we want to approximate, and this is the distribution that is the output of the generator. And step by step it becomes closer to the real distribution. Well, I think that in this case, because we can't approximate properly, we should increase the number of parameters in the discriminator. Let's do it. So let's set not 16, but say 64 here. And again, restart kernel and run all cells. Yeah, let's wait for a bit. You see that here at this point it is random, and here it is not random. It means that the discriminator learns the difference, and because of this is not random prediction, now it will change the behavior of the generator. So you see what is happening. Generator tries to change the situation somewhere here and here. So you see they are now rather close to each other. Okay, I think we can finish with one-dimensional case. In the next practical video, we will study how we can implement two-dimensional case for approximation of mixture of Gaussians, and this problem is much harder than this one. Thank you, and see you in the next video. In this video, we will modify previous practice notebook to the 2D case. Now our goal is to sample from the mixture of 2D Gaussian distributions. So now let's again import all our data. Now here we have 3 mu's and 3 sigmas, and all of them are used for the distribution generation, for the generation of samples from the mixture of Gaussian distributions. And we have here the dimension of the noise. Let's set it to 1, which it was in the previous video. The dimension of noise is here, and as I said it is 1 now. Then we have getNormal function, which is unnecessary, and I added 2 functions. First is plot 2D density in order to visualize it, and sample real data. Now here we sample from 3 normal distribution and then stack these samples. So let's look at it. Here you can see the distribution that is made by samples from normal 1, normal 2, and normal 3. Okay, now we have a generator and a discriminator from previous videos. Now let's modify it. The first thing we need to modify is that linear layer now should have an input noise dimension here, because now we assume that we can increase this dimension. Let's leave everything else the same. 16 features. Here is here as an output we should set 2, because now we work with 2-dimensional data. And discriminator as an input also obtain 2-dimensional vectors and transform it to 1-dimensional to the vector of probabilities. Okay, this is the same. The function for updating D and G is the same. Then let's look what is happening. So getNormal is now real samples is sample real data. I should change getNormal function here, and that's all. Yes, and I hope it should work. Yes, it works. And here you have real data, and here you have generated data. So it has the same scale as you see from -15 to 15 for y and x. And now you see how this generated distribution tries to approximate this distribution. I think it is rather hard for the GANs. Now let us increase the noise dimension. We should just try 2, for example 2, and run everything else again. Okay, it again starts from some points here. Now, what can you see here and what I wanted to demonstrate you? As you can see, here we have 3 modes of our distribution, because this is a mixture of 3 Gaussian distributions. But here you have samples only from one mode of this distribution. So that is located in -5, 5, which is this one, and not from any other. This is what people call mode collapse. And I show you this practical case because it is really important topic, and usually it can happen not only with mixture of Gaussians, but even if you generate faces, for example. And in some of the next videos, we will study how we can avoid mode collapse and what we can do with it, why is it so, and so on. So this is all for this video. Thank you and see you in the next one. In this course, we study convolutional neural networks. However, we should understand why we have to use them, why not to use just linear layers. Quite an obvious question. Why not to use linear layers with images? After all, we can just reshape our image to vector and do a forward pass through a set of linear layers with non-linearities. Good idea, but if our input image has 3 channels and size 256 to 256, after reshaping we will have a vector of size around 200,000. That's the main motivation for introducing convolutional neural networks. Too much parameters in the linear layer. Before we start learning convolutions, let us consider some assumptions. Could you agree with me that the closed pixels have closed values? Actually, if we consider the pixel on the cat, which is red, with high probability closed pixels will be also red. Okay, so we don't need a separate neuron for each pixel. The open question for now, how we can reuse the parameters of our network. If we don't need a separate neuron for each separate pixel, we should use one small linear layer for local regions of the image, and this is a basic idea behind convolution. We understood why we should use convolutions instead of linear layers for images. Let us now consider convolutions in details. Let us look at the visual explanation of the convolution. Again, we have an input image of size C to H to W, where C in the number of channels, H and W is height and width correspondingly. We introduce convolution's weight, 3-dimensional matrix of size C to K. Here it is. The number of channels is the same in the input image and in the weight matrix and equals to C. We use convolution weight for sliding over the image, taking the element-wise product of the local region of the image, which is green, and the weight 3-dimensional matrix, which is blue. We sum up the result of the product and obtain one value. We write it to one of the values of the output 3-dimensional matrix. We repeat this action several times with different filters. Yellow, red. In fact, convolutional operation consists of several kernels. Convolutions were popular before deep neural networks and was called filters. On the slide you can see the result of applied Gaussian filter to an image. You can see that depending on the parameter of this filter, the image lost its color and became blue. Convolution is an operation which can be represented as a layer in a neural network. That is why you can combine several convolutional layers into one neural network. Let me demonstrate the main advantage of convolutions against linear layers. Assume we have an input image with 3 channels of size 256 to 256. We want to obtain 100 output features after the first layer. Then, using linear layer, we will obtain 19 millions of parameters. In the same time, 4 convolutional kernels will have only 300 parameters. Now you see the difference. In the next video we will go deeper into convolutions. Thank you for watching. Convolution operation has several parameters. Let's discuss the most important: stride and padding. The first parameter of the convolution is its stride. The default value of the stride is 1, which means that our kernel is moving from left to right and from top to bottom by 1 pixel. On the animation on the slide you can see how the convolution with stride 1 works. In the animation, the red is a kernel, the green is the input image. Note that if we have input size 4 to 4, kernel size 2 to 2, then the output size will be 3 to 3. Now let's increase the stride to 2. Look what now happens. We increased the stride and the size of the output of the convolution decreased. Now it is 2 to 2. That is why on the first layers of the network it is better to use stride more than 1 in order to downsample input images. Okay, now let's set the stride to 3. What will happen? Probably, in this case, PyTorch will return an error. This is because the size of the image, which is 4, can't be divided to the size of the kernel, which is 3. I hope you understood what is stride, so now let's switch to another parameter, padding. Look at the image on the left. If we apply convolutional layer to it, we will obtain an equal contribution of pixels to the result of the convolution. Green pixels will play their role more than blue pixels. If we want to make the contribution of pixels equal, we could add zeros on the border of the image. And here you can see how it looks like. Red pixels have now value 0. Another reason for the padding is that we consider on the previous slide. If our image size is not divided by the kernel, we can always extend the image with 0 padding. Another possible variation of padding is mirror padding, which is in the PyTorch is called reflection padding. In this case we add not 0 pixels, but we reflect the border pixels as it is on the slide. Well, this is all for padding. Thank you for watching and see you in the next video. In this video we will talk about how we can perform upsampling using convolutional layers and transposed convolutional layers. Here you can see the architecture that we already studied, deep convolutional generative adversarial networks. And if you can see what we are doing here, we transform the input noise through some layers in order to obtain image, and on each layer we increase the spatial size of the image and decrease the number of channels of the image, and at the end the number of channels is 3. Now, how we can do it? We know that when we use standard convolutional layers we decrease the spatial size of the image. But how we can increase it and use it inside the generator network? What we in fact want is upsampling, and there are some methods that perform upsampling, such as nearest neighbors, bilinear upsampling, linear upsampling, and some others. All of them are used in standard image editors like Paint or Photoshop. However, we would like to make this upsampling learnable. So we want this upsampling to have some parameters like standard convolutional neural networks that we could learn with stochastic gradient descent. Here you can see the example of convolution operation. Blue is the input image, and the dark blue is the kernel of the convolution. The white is the output, so you can see that we decrease the size from bigger one to smaller. How we perform it? So on forward pass we have a yellow kernel and it applies to our image and we decrease the spatial size. But in backward pass we start from the small output and do a backward pass to the big input. So in fact, in backward pass of the convolution, we increase the spatial size of the image from 2 to 4. In fact, when designing these convolutions for generator, for GANs, we would like to do something that is like in backward pass. We can do two methods here. The first is to use stride 1 but increase padding a lot. The second one is not to increase padding a lot, but to use stride that is equal to half of the one. It means that we will insert some empty pixels, some 0 pixels between existing pixels. In fact, that is what we want to do. However, this is rather inefficient technique, because if we will do this each time, we will wait for a lot of weeks until our training will converge. Convolution operation usually performs as matrix multiplication. Here you can see at the top the kernel, which transforms to a convolutional matrix, and if the kernel is 3 to 3, it is transforms to convolutional matrix 4 to 16. So you can see how it is usually done. All this stuff is done in libraries such as PyTorch or TensorFlow, so all convolutional operations are performed using matrix multiplication. We transform kernel to convolutional matrix, then we transform our input image into a vector. So this is input image 4 to 4, and the vector is 16 to 1. After that, in order to calculate the convolution result, we just do a matrix multiplication with matrix of weight, which is our convolutional weight, and input, which is our image. Then we obtain a vector and transpose it back to an image, back to a square. And in fact, this is how convolutions usually performed. Now, what we can do, we can just transpose this convolution. We transpose convolution matrix, and for the small input of size 4 to 1, we obtain the big output 16 to 1, which we can then transform to an image 4 to 4. So you see, we just transpose the convolution, and this is how we can increase the size of the input image. And this is what, in fact, usually people call transposed convolution. And these layers are usually used in generative adversarial networks when working with images. Thank you, see you in the next video. Now let us talk about the paper called Deep Convolutional Generative Adversarial Networks. This was the next valuable work after Goodfellow's work and was designed specifically for image generation. The main idea of the paper is that convolutions in both discriminator and generator allows to generate more realistic images. Here on the slide, you could see the structure of the generator, which consists of transposed convolutional layers, which we will consider in the next video. Here you can see the examples of generated bedrooms of size 64 to 64. Some of them are quite realistic. However, it is easy to say whether the image is real or fake. Here are the examples of generated faces, again of size 64 to 64. For the 2015, this result was amazing. The value of the DC GANs paper is in the set of recommendations for training. These recommendations are: you shouldn't use max pooling, increase stride of the convolution instead. Transposed convolutions are good for upsampling in the generator. It is better to avoid fully connected layers. Batch normalization helps a lot. Use ReLU in the generator and leaky ReLU in the discriminator. All of these recommendations were obtained empirically. Authors just tried and obtained results. However, it allowed to significantly boost the generative learning forward. Authors demonstrated an interesting interpolation experiment. They took two vectors from the latent distribution. For both these two vectors, they generated an image just making forward pass through the generator. After that, they created an interpolation in the latent space from the first vector to the second. On this interpolation line, they took several vectors and again generated images from them. And the effect was the following. While we manually make the interpolation in the latent space, the interpolation also occurs in the images space. And it means that the generator made our latent distribution meaningful for him, despite it is random. In fact, this is a good test that shows that the generator doesn't remember images from train set but generates new sample. Here is the same interpolation experiment for the bedroom's images. You can pause the video and look at the pictures in details. Okay, what if we want to perform some arithmetic operations on our images? For example, what we should obtain if we subtract a man from a man with glasses and add a woman. Seems that we should obtain a woman with glasses. But if we do this in images space, we will obtain some noisy rubbish. The good news is that we can perform meaningful arithmetic operations in latent space. So what we do here? We take one latent code that transforms by the generator into a man with glasses, one latent code that transforms to a man without glasses, and one latent code that transforms to a woman. After that, in latent space we perform the following. We subtract from the vector for the man with glasses the vector for the man without glasses. Then we add a vector for the woman without glasses. Thus we obtain a new vector in the latent space. And if we make a forward pass with this vector, we will obtain an image with a woman with glasses. In other words, our arithmetic operations in the latent space becomes meaningful. We can perform the same arithmetic operations in the latent space with images of smiling woman, neutral woman and neutral man, which will give us a smiling man. So that was all for deep convolutional generative adversarial networks. Thank you for watching. See you in the next video. Now we're going to talk about measures of quality for generative adversarial networks. Could you please tell me if these images are real or fake? Some of them are quite realistic, aren't they? And yes, you're right, they are all generated. But how about these images? Do you think any of these images real? Or all of them are fake? And if you pause the video, you could mention that despite the very good quality of these faces, some hair are like plastic. And yes, all these images are fake. I'm not going to ask you about these images. They are all synthetic. Looks quite nice, right? So how you define if the image is good or not? How do you know if the image is close to the real samples or not? Well, you have a neural network in your head, but how we could measure the quality of generated images? Is it possible? And the answer is yes, and we will study how to do it. So, why do we need the measure of quality for GANs? Firstly, we should have some way to compare different models with different hyperparameters, such as number of layers, layer types, and number of parameters. Secondly, when we train GANs, we should have an indicator of quality in order to stop training in the right time. Last but not the least, if we write a research paper, we should somehow compare our model with existing. It is very bad practice to say, our generated cat is better than others, without providing any numerical comparison. We want our measure of quality to correlate with two aspects. First, what is the quality of our synthetic images? How good are they? And second, how diverse is our generated set? Does it cover all image classes, or it generates only one image each time? The second matrix requirement is very important. When training GANs, there exists a problem of mode collapse. Look at the top image on the slide. Our target distribution is a mixture of Gaussians, which you can see on the right. It has several modes, but at different epochs of training, our GANs model will generate samples only from one mode, but not from all of them as we expected. This is what people call mode collapse. Considering images, if we train our model on Moniz dataset, the mode collapse will be if the model starts generating only one digit. That is why it is important that our measure of quality could manage this. As I said a few slides ago, our brain has a neural network that decides whether the image is real or fake. The methods that people use for distinguishing real and fake images also use their own network. It is called the inception network, also known as GoogleNet. It was trained on the ImageNet dataset, which consists of around 14 millions of images of 1000 classes, such as dogs, cats, mushrooms, airplanes, and so on. Let me briefly remind you what is entropy of the distribution. The entropy is a measure of randomness of the distribution. It means that the more the distribution is uniform, the higher will be the entropy. And vice versa. If the distribution is concentrated in one point, it will have the smallest entropy 0. As you can see on the slide, the entropy of P2 distribution will be higher since it is uniform. The distribution P1 is more concentrated. The first measure of quality is inception score. Firstly, we use inception network for predicting the distribution P of y given x. This is an output of the last softmax layer of the inception network. We want this distribution to be highly predictable. In other words, we want it to be concentrated in one point. It means that we want the entropy of this distribution to be lower, and this stands for the quality of an image. The more concentrated is our image, the more confident is the network in the prediction, which is good in terms of the image quality. Okay, we understood that we want the entropy of the distribution P of y given x to be lower, and it stands for image quality. Now we have to do something with image diversity. For this reason, we can consider P of y distribution. We want it to be uniform, which means that we want the entropy of P of y to be higher. Now, how to calculate P of y? We should generate a lot of images. For each of them, make a forward pass through the inception network and predict P of y given x. Then we need to average our prediction distribution by x, by our images. X is our images. Thus, we will obtain the distribution for P of y. Look at the picture on the slide. Here is the demonstration of our wishes. We want P of y to be uniform and P of y given x to be concentrated in one point. From the probability theory, we could remember that Kullback-Leibler divergence between two distributions is the difference between the cross entropy and the entropy. Taking into account the fact that we want the minimization of the first entropy and the maximization of the second entropy, we can combine them into a Kullback-Leibler divergence, and here we obtain inception score. It is defined as the KL divergence between two distributions, P of y given x and P of x. And now you know how it was obtained. Note that the higher the inception score, the better is our GANs model. Now let us discuss the second measure of quality for GANs, Fréchet inception distance. As you can guess, it also uses inception network, but in a different way. Firstly, we use inception network for feature extraction for both synthetic and real samples. Then we assume that the obtained features are distributed as a multivariate Gaussian distribution. Then we estimate their mean and covariance matrix. We do this both for real and synthetic images. Then we compute FID with the equation on the slide, as the difference of means and the trace of the square distance of covariance matrices. The lower Fréchet inception distance, the better is synthetic image quality. Fréchet inception distance was shown to be sensitive to mode collapse, which is good for us. When our generator sample images only from a subset of classes, the FID starts increasing. Let us now compare the inception score with Fréchet inception distance. Both of them correlate with human assessment. However, inception score doesn't take real samples into account at all. If our generator samples only one image per class, then the inception score will fail and show high score. FID is sensitive to it. The disadvantage of the FID is that if we take two different batches from the train set, then FID will be non-zero, which is not good. And both these two metrics have a common disadvantage. They can be applied only to photo-like images like cats, dogs, airplanes, or anything. If you generate specific images like MRI or textures or any medical data, then these methods are inapplicable. The last measure of quality that I would like to discuss is geometric score. It is based on the manifold hypothesis and applicable to any kind of data. If you want to use it, use the link to the GitHub from the slide. It is all for measures of quality. Thank you for watching and see you in the next video. Hello, my dear friend. In this video, we will study how we can implement deep convolutional generative adversarial networks in practice. I took all the code from the official PyTorch tutorial, and in this video I want to comment it to explain each line of code to you, and I hope that after this video you will be able to build DC GANs by yourself. So the task for this tutorial is to generate faces, and now let's import necessary libraries, and here we have some settings. What we have here, we have data root, we have number of workers for PyTorch dataset, it's the number of processes that load our dataset from data, we have batch size, we have image size. We will work with Celeba dataset, which has images of size 64 to 64, and we will train our network to generate images of size 64 to 64. Next, the number of channels. We have 3 channels, red, green, and blue. Then NZ is the size of the latent space, of the latent vector. So we will generate the noise of size 100. Here is the size of feature maps in generator and discriminator. You will see a bit later what it is. The number of epoch of training, learning rate, beta 1 parameter which is used in Adam optimizer, and the number of GPUs. So now what we do here, we load our data from some folder. Our data is located in data root, which is current directory. Then we apply transformation, which is resize, then center crop, then to tensor and normalization. When we do resize, we just resize all images to the size 64 to 64. Then when we do center crop, we crop the central part of the image. Then we convert this image to tensor, to PyTorch tensor, and after that we normalize. Here we path mean and standard deviation, and it means that after this normalization our mean will be 0 and our standard deviation will be 1. After that we should path this dataset to the data loader with batch size. We want to shuffle our data, and I always recommend you to shuffle the data, and the number of workers that we defined in previous cell. After that we define the device, which in our case will be CUDA, and here is some visualization of our data. So you can see what training images we obtained. This is faces of celebrities. For example, I can see here Harry Potter and other different celebrities. Now, here we have weight initialization function. It is a bit different for convolution and for batch norm. For convolution, we use normal distribution with 0 mean and close to 0 standard deviation. And this is rather practical recommendation that was shown to be rather good initialization method. And for batch norm, we initialize the weight data is standard deviation with 1 and bias with 0. Remind you that in batch norm we have two parameters, learnable mean and learnable standard deviation. So here we set learnable mean to 0 initially and learnable standard deviation to 1, to random number near 1. Okay, and here we have a generator. So here we have a set of transposed convolutional layers, batch normalizations, and ReLU layers. Let's look at first transposed convolution. As the input number of channels, we have NZ, which is in fact our latent space. So the input here will be our noise. And the output number of channels is NGF dot 8. NGF, I promised you, it is the size of feature maps in generator, so it is 64, and for the discriminator we again have 64. So it's just a parameter that we define, so here you just set 64, 64, 64, and so on. Then the size of the kernel is 4, the stride is 1, and the padding is 0. After that, we make batch normalization in two-dimensional space because we work with images. Again, ReLU, convolution, batch norm, ReLU, and so on. And notice that as an output, we have hyperbolic tangent here. It means that all our images will be from -1 to 1. And this is important, in fact, because when you usually work with images, all values of pixels should be in the range from 0 to 255, which stands for pixel intensity or color intensity, or from 0 to 1, which can be transformed to the range from 0 to 255. However, here we have from -1 to 1, and this is just practical case, and in the paper Deep Convolutional Generative Adversarial Networks, authors showed that hyperbolic tangent as an output layer is the best for GANs. Here we initialize the network, make it parallel, and apply weight initialization, and you can see what is our neural net looks like. The same we do with the discriminator. However, notice that now we have as an input number of channels, then NDF, NDF to 2, NDF to 4, and so on. And again we have convolution. Now leaky ReLU instead of just ReLU. It's just again practical case that authors of the paper studied, and again and again, and also with batch normalization. We again initialize the discriminator, and now we define the last function, which is binary cross entropy loss. In previous videos, in practice, I showed you how we can implement this binary cross entropy by our hand for GANs, using probability of the image of the object to be real or to be fake. And now we can just define binary cross entropy loss from PyTorch. Then we have some fixed noise that we will use for testing on each iteration. We just sample it once from standard normal distribution, and we fix it. Then we establish some class for real object, which is 1, and for fake object, which is 0. And we also have here two optimizers, for the discriminator and for generator. And here is our parameter beta1, which is 0.5, and which is again the recommendation from the DC GANs paper. I think this is all for this video. In the next video we will discuss training of this network, and we'll look at the results. Thank you. Now we have the training loop for our DC GAN. Let's run this cell, and while it's running, I'll explain you what is happening here. So we have three lists for losses and for images. We have iterator for iterations. And here we have number of epochs. One epochs mean that we will see each of the images once. So this is one epoch. And totally we have 5 epochs. Then for each epoch we do the following. We have 2 main blocks, updating of the discriminator and updating of the generator. When we update the discriminator, we first do update with real samples. So what we do here, we obtain some data from data loader, then we transform it to device, which in our case is GPU. Then we set the label to real label, which is 1. Then we obtain probabilities of these real samples to be real and call the criterion, which is in our case, remind you, binary cross entropy. Then we do backward pass and compute the loss value. In fact, we do the same as we did in one-dimensional or two-dimensional cases. The difference that now we use predefined criterion, but it is in fact the same. Now we update the discriminator with fake batch. For this, we take some noise from normal distribution with NZ samples 1 to 1, and 1 and 1, this is spatial dimensions of this noise. And this is like number of channels. In fact, this is not an image, but you can look at it as an image. So we have dimensions batch size, then noise dimension, which can be interpreted as a number of channels, then height and width. So this is our like input noise image. And then we call generator function, set the label to fake, then we obtain the output of the discriminator on these fake, in other words, generated samples. And also compute the criterion, do the backward pass, compute mean loss value, then we sum up real error and fake error, and do the step of the optimization. So again, we do the same as we did in one-dimensional or two-dimensional cases. Now we have to update the generators network. We should maximize the probability of fake sample g of z to be real. This is the case for generator. What we have here, we again have the same fake images, we compute the discriminator, but we set the label to real label. So here we set it to fake label, and here it is real. And compute the same criterion, do backward pass, compute loss function, and do the optimization step. Note that the discriminator is updated using real and fake samples, but generator is updated according to the discriminator loss only on real samples and with mixed labels, so not fake here but real label. Here we have the print of the loss values, and here we just visualize some images and append it to some predefined array. Now let's wait until the training will finish. Our training was finished, and now let's look at the results. So here you can see the loss functions for the generator and for the discriminator. Now we have the visualizations of images starting from the first iteration and until the last iteration. And here we can do the following and we obtain the animation. Here we use fixed noise in order to obtain these images. So all these images were generated from the same noise. And you see how the quality of them improves from the iteration to iteration. So yes, here's the final. And again, at the beginning of the training, the generator outputs something like noise. And now we can compare generated and real samples. So you see that it is rather easy to distinguish between real and fake samples. However, they are quite nice. We can scale. You see some artificial stuff here, but I think it's rather nice result. In next videos we will study how can we generate really good samples, really high quality images. This is all for face generation practice. Thank you. In this section we will talk about applications of generative adversarial networks. On the slide you can see total number of papers for generative adversarial networks that was published since 2014, and in fact this image was taken from one of the GitHub accounts that host all these articles, but I think there are much more articles, maybe around 1000. And of course it's usually hard to analyze what is useful work, what is not useful, because everybody wants to develop their own model. And in this section I tried to select the most valuable works and the most valuable applications that can be applied in either business tasks or just interesting and useful for further GANs development. Now, the first modification or application of GANs is conditional generative adversarial networks. So, I already told you that the generator, which is blue on the slide, usually takes some noise from uniform or normal distribution as an input. The difference of the conditional GANs from standard GANs is that we also put some class label as an input to the generator and to the discriminator, which is green. This usually helps when we want to generate an image of a given class. For example, if we would like to generate images of handwritten digits, then we can use digits from 0 to 9 and stack them to the noise vector as I showed on the slide. And this allows us to generate conditionally to generate an image given the class label. Now I want to show you really useful application of GANs for pre-training. Again, we have a generator which is blue and a discriminator which is green. And imagine you have a set of images which are all unlabeled, so you don't have classes for them. But your final task is to solve some classification or regression problem, so you need labels for your target problem. However, let us first train generative adversarial networks that will allow us to generate images that are similar to those in your dataset. After that, what we do? We take the discriminator and we remove last 1 or 2 layers. We just remove them and we can add new layers at the end of the discriminator and train these 2 layers on the label data that you have. For example, if you have very few labeled data and a lot of unlabeled data, this should work. And this is very similar to what is called transfer learning, when you, for example, take some some pre-trained neural network which was pre-trained on big dataset like ImageNet, and after that you remove last layers, you add new one, and you train this new one on your small existing labeled dataset. So this is very useful, and we can also apply GANs here. Another possible application is supervised discriminator. So what is proposed? We have a discriminator, and instead of just classes real and fake, we divide the real class into subclasses like cat and dog. And if we classify cat and dog, now we have three classes: real cat, real dog, and fake images. And when our GANs are trained, we can take again this discriminator and use it for our supervised task like classification of cats and dogs. This is all for this video. Thank you for watching, and see you in the next video. In this video, we are going to study cycle GANs, which was published in 2017. Here you can see the examples of the cycle GANs model. Its main purpose is to transform image to image. For example, the first examples show the transformation of the images of Monet drawing to the photo and back. Second example demonstrates zebra to horse transformation. On the third example, you could see how summer becomes winter and winter becomes summer. Finally, on the bottom, you could see the transformation of the photo to styles of different artists. All these examples was made using cycle GANs. And in this video, we will study how it works. The distinguishable feature of cycle GANs is its unpaired mode. It means that we don't need any mapping from one type of images to another. In case of cycle GANs, we need only two sets of images, and the model itself learns the transformation from one set to another. In the example on the slide, you only need a set of photos and a set of drawings in order to train the model. The places on the photos shouldn't be the same as in the set of drawings. Cycle GANs consists of 4 neural networks, 2 generators and 2 discriminators. Note that we don't have any input noise here. Since we have 2 types of images, A and B, we have a separate discriminator for both of them and a separate generator again for both of them. We start from the image A, which is a horse in our example. The discriminator A will tell us if the image is of type A or of type B. Again, the difference from the standard GANs is that there is no real or fake classes. Now we have 2 classes, type A and type B. The image A is an input for the discriminator A, which decides whether the image is of type A or B. Then image A is an input for the generator A to B, which transforms a horse into a zebra. After that, the discriminator B decides if this image is of type B or A. The generator A to B tries to transform the input image to type B such that the output will be indistinguishable. In this model, we also have a generator B to A, which transforms zebra back to the horse. This was the first part of the cycle GANs iteration. Now let's continue with another one. We start from the image B as an input. Now discriminator B decides whether this is a horse or a zebra and tries to distinguish them. Then image B becomes an input for the generator B to A, which transforms it into a horse. Discriminator A decides whether it is a horse or a zebra. After that, image A again transforms to an image B with the generator A to B. The goal of the generator A to B is to transform image of type A to an image of type B in such a way that the discriminator B will fail in distinguishing it from real images of type B, and vice versa. The goal of the generator B to A is to transform image of type B to an image of type A in such a way that discriminator A will fail in distinguishing it from real images of type A. In our model, we have two adversarial losses, which stands for two discriminators and one pixel-wise difference loss. The goal of the adversarial loss is to help generators learn proper transformations. Pixel-wise difference loss stands for the ability of generators to reconstruct image from type A to type B and back. Now let's look at some examples from the GANs paper. Here on the top you can see the transition of a facade to its labels and back. On the bottom, sketches are transformed to the realistically looking shoes. The GANs model is able to transform paintings to photos and photos to paintings, horses to zebras, zebras to horses, and even oranges to apples and back. Nice application is in season change. The model is able to transform images from winter to summer. It may find its application in film development, where usually it is required to be summer, but the film is made in winter. The last nice application of GANs model is background blurring. GANs are able to detect the object in the front of the picture and blur everything else. Well, now you know how it works in model mobile phones. This is all for this video. Thank you for watching and see you in the next video. In this video, we will study how we can apply generative adversarial networks for the problem of super resolution. If you don't know what is the problem of super resolution, here is the example. The left image is your input image, and imagine that you would like to increase its quality, so you would like to increase its resolution. If you just use some graphical editor like Photoshop or Paint or any other, which use not deep learning techniques for super resolution, but some standard interpolation methods such as bicubic interpolation or nearest neighbors interpolation, then you will obtain very bad results where you will see the pixels on the photo. However, if we use generative adversarial networks, we can obtain very high quality images of higher resolution. And let's study how we can do it. So here is the model of the generator and the discriminator that is used in the paper, which is called Photorealistic Single Image Super Resolution using Generative Adversarial Networks. This model works with patches from the images. Patch is a sub-image from an image. You just randomly take some part of the image and use it as an input for this neural network. In order to train this network, you should have a dataset in the format high resolution and low resolution. In order to obtain this dataset, you should take a set of images of high resolution and manually make them low resolution, and after that try to restore the high resolution images back. So you take the subset of the image and use one convolutional and one ReLU layer. After that you have B residuals, big blocks, which consist of convolutional layers, batch normalizations, ReLU layers, and element-wise sum. You use several such residual blocks with skip connections, like in the ResNet architecture that was proposed for their classification. After that you use convolution, batch norm, again element-wise sum. Then you use convolution and the interesting layer which is called pixel shuffler, and then ReLU. Here is the pixel shuffler layer explanation, what it does. In fact, if you have several channels, several filters that were obtained from the previous convolutional layer, the quantity of which we can manage with setting the parameter of the convolution, we can rearrange or shuffle these pixels into one big image. So we increase the resolution but decrease the number of channels of the input image. This is pixel shuffle layer. After that, we use again one convolutional layer and obtain super resolution patch. So we have low resolution and here we have super resolution patch. The structure of the discriminator is a bit easier. It also consists of convolutional and leaky ReLU layers with batch normalizations. It also works with patch, and as an output it decides whether the patch is high resolution from the dataset or it is super resolution, in other words generated or synthetic. Note that we again don't use any noise as an input to the generator here. We just use the patch of the image. Now, in order to construct the final loss function, we need to know what is VGG network. VGG is a network that was proposed for classification, but it is good as a feature extractor. And authors use this network for the constructing loss function. What they actually do, they take each image as an input to this network and they take the features from the last layers, and here is how they can use it. So they extract features from high resolution image from the dataset, and also they extract features from generator from low resolution image. So this is high resolution original from the dataset, and this image is synthetic, but also it is super resolution. And they took the square difference between them, which is Euclidean loss. They average it over the images, and this is what called content loss. The second loss that they use is adversarial loss, which is a standard loss function for the generative adversarial networks that we have already studied. And in order to combine content loss and adversarial loss, they just sum up them with the 10 power minus 3 in front of the adversarial loss. And here is their total loss. You can see the result. This is low resolution image, and you see the quality of this animal. Here is the high resolution ground truth. You can see bicubic interpolation, which is usually used in standard image editors, and super resolution GAN that they proposed. So you see the quality is almost indistinguishable from ground truth. Here you can see again the result on the other image. Here is the bicubic interpolation, which is rather bad. Here is previous work from different authors. Here is their work and the original, and you see they are almost indistinguishable. However, there is a bit difference between these images. So that was all for super resolution GANs. Thank you. See you in the next video. In this video we will talk about the problem of inpainting of images, and I will describe you page-based approach using generative adversarial networks that was proposed in March in 2018. Here you can see what is inpainting is, and you can see the results of the work that we will discuss now. The task is to given an image with a hole to fill this hole with something. Usually we as a human can just guess what it can be behind this gap in the image. However, we expect that neural network will learn the same that we know, and for example, at the left upper image we can guess that there should be a balcony, and the neural network also puts balcony instead of this gap. Now let's talk about the model. So at the left there is a generator and on the right there is a discriminator. The generator consists of residual network, ResNet, which was originally used for classification, but they used it also and add several convolutional layers. The interesting thing about their work is the discriminator. So how it works? As an input, we put some image with holes like you see in the left on the slide. There can be several holes in fact. And after that, we construct a discriminator in such a way that formally we have two discriminators. One global discriminator that decides whether the full image is real or not, and a patch discriminator, which predicts a vector of probabilities where each element decides whether the given patch is real or not. Let's look at it in details. So here you can see what I was talking about. We have some patch at the input image, and it corresponds to one element of the output vector of the discriminator, and this is the probability of this patch to be real. Note that they split patch discriminator and global discriminator only at the end of the discriminator, and several first layers are the same and they have the same weights. They are shared weights. They train differently only global and patch part. Now let's talk about the loss function. Here is the total loss function, which consists of reconstruction loss, of adversarial loss for global discriminator and adversarial loss for patches. And there are three parameters which are hyperparameters: lambda1, lambda2 and lambda3. They use standard GANs loss, which is binary cross entropy, and they use it the same for patch and for global version of discriminators. As a reconstruction loss, they used pixel-wise L1 difference, which is averaged over all images over all pixels. After that, they sum up it with some coefficients lambdas. Here you can see the result. At the first row there is an input image, on the second row there is an output image. So we can see that yes, there are some defects on the photos, however it is rather nice results. Again, some results. A knife. Some building, and you can see artifacts. and a bagel. Thank you, that was all for In Painting with GANs. See you in the next video. In this video we will study how we can generate images from their text description using generative adversarial networks. Here is the example of these generated images from their text descriptions. You can see the images of the generated birds and flowers. Now let's look at the model that the authors of the paper proposed. In fact, this is a standard conditional deep convolutional generative adversarial network. However, there are a few details, and let's look at them. The first thing we do is the encoding of the text description. For this purpose, we can use embedding layers, convolutional and recurrent neural networks. I will not go into details about encoding the text. However, you should understand that we transform our text description into a vector representation. If you want to look at the details, please read the research paper that I mentioned in the right bottom corner. After we obtain the vector representation, we stack this vector representation to the noise vector which was generated from the standard normal distribution. After that, we use a set of transposed convolutional layers or deconvolutional layers in order to transform this input vector into an image. And this is our generator. The same generator was used in Deep Convolutional Generative Adversarial Networks paper that we studied in the previous section. Now the discriminator takes as input the image and at the first layers transform it into some representation. After that, we stack again, as in the discriminator, we stack the encoding, the embedding of the text description to this image representation. After that, we use convolutional layer in order to transform this image and text to the label fake or real. And this is the discriminator network. Now let's talk a little bit about the algorithm of training. For each iteration, the first thing we do, we take the two batches of text. First is match text description and second is mismatch text description. It means that for the given set or mini batch of images, we have the text that describes this mini batch of images and the set of texts that don't describe this mini batch of images. This was done for the reason that authors want to somehow distinguish two situations: when the generated image corresponds to the input text and when it's not correspond. That's why we have two text description sets. After that, we sample the noise from the normal distribution and make a forward pass through the generator of this noise and the matching text description. After that, we have three situations. We can obtain real image with correct text, real image with wrong text, and fake image with right text. Note that we can't obtain fake image with wrong text because we don't know what is wrong or right. After that, when we compute discriminator's loss, we use these three cases. First is real image and right text, and second is real image wrong text or fake image right text. It means that we can consider two different types of errors. And in fact, here in the formula, we take the average of these cases. It means that we take into account both cases, when the image is real but text is wrong, and when the image is fake but text is right. On the next line, we make an update of the discriminator with stochastic gradient descent or any its modification. Then we update the generator using fake image with the right text, and again make a step of the gradient descent algorithm. Here you can see the examples that was made using this model. GT stands for ground truth and ours means the model that the authors proposed. You can see these images are a bit realistic, however they are not very high quality. In the next section we will consider models that allows to generate images of very high quality. However, this work was made in 2016 and at that time people were unable to generate high quality and high resolution images. This model also can be used for style transfer. We assume that our Z contains the information about the style of the image. And that's why the authors propose to introduce the third neural network, which is called encoder, that takes an image as an input and then transform it to the input noise again. So we take some noise, then make a forward pass through a generator and then make a forward pass through the encoder S and obtain Z again. We do this by minimizing the square distance between the input that and the output that. And we do all this after we have already trained the generator to generate realistic samples. And then, if we want to transfer a style from one image to another, we firstly use this encoder to obtain the Z, which is now not the noise but the style, and then pass this Z to the generator instead of the noise and generate new image X hat. Here you can see what I'm talking about. We have some text description and we have a set of images which we consider as style image. Now, for example, we take this first bird, then we make a forward pass of this image through the encoder and obtain a noise, but it is not a noise in fact, it is some style, and path it along with the encoding for this text to the generator and obtain this image. Now, changing the styles, we can obtain the same bird but of different styles, as you can see on the picture. So, considering columns, the styles are similar, and consider the rows, the birds are similar. So that's the style transfer approach that the authors proposed in the paper. Remember that I already told you that using deep convolutional generative adversarial networks, we can make an interpolation in the latent space and obtain the interpolation in the image space. The authors proposed to do the same, but in the text encoding space. So they took two texts, T1 and T2, and make the interpolation using some linear coefficient beta T1 plus 1 minus beta T2, and make this interpolation changing beta from 1 to 0. And what they obtained? From blue bird with black beak to red bird with black beak, you can see the interpolation of the same image but changing bird. The same you can see here. For example, this bird is bright, this bird is dark. You can see how the bird transforms from the bright bird to the dark bird. This is all that I wanted to tell you about text-to-image generation. Thank you. See you in the next video.